Alright, in this video we study some basic properties of the limit of univariate functions, and these properties are very similar to those of sequences. So if you notice the similarities and differences, it may be easier to understand. Okay, let's start. Okay, in the following we assume that the limit of two functions, f of x as x goes to a is alpha, and another function, limit of g of x as x goes to the same a, and that is beta. Okay, we assume this. Then, the first property is linearity. That means for any k and l that are arbitrary real numbers, we have the following. So limit as x goes to a, the linear combination of these two functions, k f of x plus l g of x, is, so the limit of a linear combination of functions is the linear combination of the limits. So that is k times alpha plus l times beta. So limit of a linear combination is linear combination of the limits. So let's prove this. And since we're assuming these two limits, that means for any epsilon, let's consider f of x first. There exists, let's say delta 1, such that for all x, and we implicitly assume some domain for f and g that are overlapping. Okay, so without specifying any set here, we just assume some domain of f. For any x, if x minus a is between 0 and delta 1, then the difference between f of x and alpha is less than epsilon. And similarly, we can assume for all epsilon that is positive, there exists some, let's say, delta 2, such that for all x, if x minus a is between 0 and delta 2, then the difference between g of x and beta is less than epsilon. So these are the consequences of our assumption here. And from this, we derive this. Okay, so now let's define delta as minimum of delta 1 and delta 2. So that means if the difference between x and a is between 0 and delta, then we have both differences. F of x minus alpha is less than epsilon, and g of x minus beta is less than epsilon. Okay. So let's take the difference between the linear combination of the functions, k times f of x plus l times g of x, and take the difference between this and the linear combination of the limits, k alpha plus l beta. Okay, so this is equal to k of f of x minus alpha plus l of g of x minus beta. And using the triangle inequality, we have k and f of x minus alpha and l and g of x minus beta. But we have these two inequalities, so this is less than k epsilon plus l, absolute value of course, epsilon. So that is k plus l times epsilon. But epsilon is any positive real number, so this constant times epsilon is also arbitrarily positive constant. So that means the limit of the linear combination of these functions is the linear combination of the limits. So therefore, this linear combination converges to k alpha plus L beta as x goes to a. And we are done. And next property is this. The limit of a product as x goes to a is the product of the limits. And here, of course, we're assuming that the limit of f of x is alpha and the limit of g of x is beta, both as x goes to a. So let's prove this, and let's see. So again, let's take delta as minimum of delta 1 and delta 2. And delta 1 and delta 2 are the same delta 1 and delta 2 as we have used here. Okay, so this is assumed. Okay, so let's take the difference between f of x times g of x minus alpha times beta. Okay, so let's see. F of x, g of x. Let's say f of x times beta plus f of x times beta minus alpha beta. Okay, and using the triangle inequality again, we have f, so this and this, f of x, and let's see, g of x minus beta, and plus this part, so f of x minus alpha times beta, absolute value. And so this is less than epsilon, and this is less than epsilon, so we have, okay, no equal sign here, f of x times epsilon, and this is less than epsilon and beta. Okay, so we have epsilon times f of x plus beta. Now we still have something that is moving here. So we have f of x here, and we want to get rid of it. Now, because f of x converges to alpha, we have f of x minus alpha. The absolute value is less than epsilon. So that means negative epsilon, f of x minus alpha is between negative epsilon and positive epsilon, and that also means alpha minus epsilon less than f of x less than alpha plus epsilon. Okay, so that means the absolute value of f of x should be less than the maximum or minimum. Which one is it? Maximum. Maximum of the absolute value of this or this. Okay. So that means this thing should be less than epsilon times, let's say maximum of this as some constant m. Then this should be less than epsilon times m plus absolute value of beta. And they are both constant. M and beta are constant, and epsilon is any positive real number. So that means this difference between the products is less than an arbitrary positive number. Arbitrary positive number, where is it? Here. Therefore, we just prove the convergence of the product to the product of the limits. Therefore, f of x times g of x converges to alpha beta as x goes to a. And next property is that the ratio converges to the ratio. Okay, so f of x over g of x converges to alpha over beta, given that beta is non-zero. Okay, and again, we're assuming that f of x converges to alpha and g of x converges to beta as x goes to a. So let's try to prove this, but this one, f of x over g of x is just f of x times 1 over g of x. So this the limit of this ratio is reduced to the limit of product of two functions. One is f of x and one is 1 over g of x. So what we need to prove is therefore this 1 over g of x converges to 1 over beta, given beta is non-zero. Okay, so if we can prove this, then we are done. Okay, so this all reduces to this 1 over g of x minus 1 over beta is less than some arbitrary positive constant. Okay, so let's modify this a little bit. So this becomes beta minus g of x over g of x times beta. And we already know that this numerator is less than epsilon. So this is less than epsilon over absolute value of g of x times beta. Okay, but beta is a constant and g of x is not a constant, and we want to show that this is less than some constant. Okay, so if this holds, then we should have epsilon beta over c is greater than g of x, absolute value. Anyway, we want to have this quantity is greater than some positive constant. Okay, so that is our goal for the moment. And to do that, we use the triangle inequality. Okay, so we have, let's say, beta absolute value is equal to beta minus g of x plus g of x. So by using the triangle inequality, we have beta minus g plus g absolute value. And however, we know that this part is less than epsilon. So that's epsilon plus g of x absolute value. Therefore, we have the absolute value of g of x is greater than beta minus epsilon. Okay, now remember that this epsilon is supposed to be a very small positive number. Okay, and it's okay to assume that this epsilon is so small that we can assume epsilon is less than, let's say, half of beta absolute value. Okay, so epsilon is greater than 0, of course, and it's so small that we can assume this is true. Okay, if that's the case, then this is less than beta minus half of beta 2, which is half of beta absolute value. Okay, so the absolute value of g of x, if x is close enough to a, is greater than half of beta absolute value. Okay, now using this, let's go back to this inequality. So this is greater than epsilon over beta over 2 times beta. So that's 2 epsilon beta squared. Okay, now beta is a constant, non-zero constant, and epsilon is an arbitrary positive constant. So that means this difference, 1 over g minus 1 over beta, is the difference is less than some arbitrary positive constant. That means we have this convergence. G of x converges to 1 over beta. 1 over g of x converges to 1 over beta as x goes to a. And we are done. The next property is about the composition of functions. Okay, in this case, unlike the previous cases, consider these limits. As x goes to a, f of x converges to b. And another function, g of x, as x goes to b, converges to alpha. Okay, so f goes to b and g goes to alpha. Then the limit as x goes to a and g after f of x, then this function converges to alpha. And of course, by the definition of function composition, this also means this. So g of f of x converges to alpha as x goes to a. So this means this. Okay, so let's prove this. First, consider this convergence. Okay, for any epsilon. So this is given condition. Okay, so given epsilon that is positive, there exists, let's say, delta 1 that is positive, such that for all x, x is in the domain of g, of course. Let's write it, domain of g. So for all x, if the difference between x and b, so here we are considering as x approaches b, is between 0 and delta 1, this implies the difference between g of x minus alpha between g of x and alpha is less than epsilon. Now, for this delta 1, delta 1 is some positive real number. So for this delta 1, there exists some delta such that for all x which is in the domain of f, if the difference between x and a is between 0 and delta, so this delta is this delta, then the difference between the difference between f of x and b is less than delta 1. Okay, so this delta 1 is this delta 1. Now let's combine all this together. So if we determine delta and delta 1 in this way, we can say that if x minus a is between 0 and delta, then we have this, and then we can substitute this f of x to this x, then we have 0 f of x minus b is less than delta 1. So because of this, we have g of f of x minus alpha is less than epsilon. So if we choose delta in this way for a given epsilon, then we have this implication. If this is true, then this is true. Then this means the limit of g of f of x is alpha as x approaches a. And we are done. Okay, so let's see a few concrete examples. Okay, first of all, limit of x as x goes to a is a, of course. This is a tautology. This is obvious. Now, from the linearity of the limit process, 2x, this limit as x goes to a is, of course, 2a. Because this is due to the linearity of limiting procedure, limiting operation. Okay, and limit of x squared as x goes to a is, this is limit of x squared, so x squared is x times x. Okay, so that means limit of x times limit of x, right? Because the limit of the product is the product of the limits. So this is a times a, which is a squared. So we can just write this as a squared, obvious. And this applies to any polynomial functions of x. And so now we have limit of x squared is equal to a squared. Now consider the polynomial. For example, x squared plus 2x. Okay, again from the linearity, then this is the limit of x squared plus limit of 2x. Both x goes to a, of course. Then we know that the first limit is a squared and the second limit is 2a. And in general, if f of x is a polynomial of x, then the limit of f of x as x goes to a is just f of a. So we can prove this in a similar manner as we have done here. First this, then this, and this for any polynomial. So x to the power of 2 and x to the power of 3 for any natural numbers. We have similar results. So therefore, we have this result for any polynomial of x. Okay, next, let's consider the limit of x cubed minus 1 over x minus 1 as x goes to 1. Okay, so if x goes to 1, then the numerator converges to 0, and the denominator also converges to 0. So we have 0 over 0. So is it 0 over 0? It's not. Because, in the previous theorem, the limit of the ratio of two functions is the ratio of limits given that this beta in the denominator is non-zero. Okay, but in this case, the denominator converges to 0, so this theorem cannot be applied here. Okay, so this is wrong. So what we can do here is, luckily, we can factorize this one. So x cubed minus 1 is x minus 1 times x squared plus x plus 1. So we can cancel this one. Okay, so this limit is equal to limit of, so if we cancel x minus 1 in the numerator and denominator, what we left is x squared plus x plus 1. So that is, so x squared converges to 1, x converges to 1, and 1, of course, converges to 1. It's just a constant. So we have 3 as a result. Okay, that's all for this video. See you later.